SwayamPrabha. Digital India. Educated India.
So we are going to start a new topics today, that's on recovery, recrystallization and grain growth. This is a different topics from whatever we have discussed earlier. We call recovery, recrystallization, grain growth as a phase transformation because new kind of grains and phases can form from a old or parent phase. That's why it is called a phase transformation. But the phase transformation is different here in the sense that this is mainly due to the defect structure in the material. So therefore, before we go into these things, we should first discuss how actually defect structure form during deformation of a material. You know, most of the materials are basically prepared in this world in the final form after different types of deformations. So we use techniques which allow us to prepare these final products. They can be either rolling or forging, extrusion, wire drawing or even drip drawing or many other things. I am not discussing here all of them. But these are the main processing techniques which are used to prepare objects which you see in the real life from in the final form. Like if you consider the fan blades, they are prepared from a steel after severe lot of plastic deformation using rolling. Similarly, many other objects. So in each of the deformation processes which will be discussed in 7 other courses, materials are subjected to plastic deformation. And plastic deformation means obviously dislocations, point defects and twinning. These are the main modes of deformations. Therefore, defect structures will be formed in the material by this process. So now once the material is subjected to this kind of metal working, or metal forming by application of the force, a lot of stress is generated. So thus they are annealed subsequently, that means they are heated to a high temperature to remove these stresses or rather to have certain kind of equilibrium situation in terms of the defects in the material. Although it is not a true equilibrium, but some sort of a adjustment in the structure, defect structure of the material after the metal forming is done. How these are done? Okay, that is the main topics. So working or forming can be done in either by hot working, like a temperature higher than about 0.5 or melting temperature of the material, like for steel, suppose melting temperature of steel is about 15 to 1600 Celsius temperature. So any temperature beyond 800 is known as hot working for the steels. So that means steel will be heated to that temperature, let us say about 900 to 1000 Celsius temperature and then deformed. So normally this is done because at high temperature the strength of the material decreases substantially. So therefore it is easy to deform. Obviously ductility increases, ductility will be quite good even at room temperature, but high temperature it will be substantially increased, and this allows us to deform the material extensively, and that is how hot working is done at high temperatures. Similarly, one can also do a cold working, that is deformation of a material at a temperature slightly above, slightly below, not above, actually below 0.3 Tm. So for steels 0.3 Tm is something like about 500 degrees Celsius temperature or 400 degrees Celsius temperature rather. 350 to 400 Celsius temperature is what is known as cold working for the steel. So many cold working processes are being important for mass productions. Normally cold workings are more preferred nowadays because we have minimum or no machining requires subsequently. So, these processes, that is why cold working are known as near net step processes. So, that is why nowadays in any steel plant, if you visit, there will be cold rolling mills. That means the steels are deformed at very low temperature. Very low means compared to the melting temperature of the steel, something like 300, 400 or even lower, to produce products, final products. So, thus there is no subsequent operations will be required. In hot working, temperatures are high, so therefore steel will get oxidized and the oxide scales forms, thus requires subsequent secondary operations to remove them or to get the final shapes using machining or some other processes. But in cold working you do not need that, and that is why this technique is widely used nowadays in the steel plants. I mean, that is true for many other metals also. Some metals it is better to use something known as warm working, not like as working at such a low temperature, but in the temperature between 0.3 Tm to 0.5 Tm, materials are heated and deformed using these processing techniques like rolling, forging, extrusion or drawing operations. So, what actually happened at this temperature, normally as you see there are a lot of things written there like recrystallization will not happen, but something else will happen. So, therefore, warm working is also another way of deforming a material at a temperature intermediate between cold and hot working. So, question is this: once we deform a material using a cold working, that is what is the paramount importance for us, but many things will happen even in hot and warm working also, whatever discussion we are going to do. When you deform in a cold conditions, that is at low temperatures or at room temperature, then materials will be accumulating what is known as a defect structures. As I said at the beginning, defect structure means they will be accumulating dislocations or point defects or twins depending on the what kind of mode of deformation happens in the material. So, therefore, main effect of this kind of working or deformation is basically plastic deformation induced defects like. So, we use working conditions definitions as cold work, as I said, which is basically, or warm working, which is basically between less than 0.3 or 0.3 to 0.5 Pm, and we always say it is either cold work or warm work. Okay. So, in both the cases a lot of defects are generated like vacancies, self-depreciation, dislocations, and this leads to decrease in the ductility of the material or increase of the strength of the material, obviously, because if there is a more number of defect structure in the material, deforming the material is difficult because it requires more force to deform it further, and that is why strength increases. Subsequently, as there are dislocations and defect structure present in the material, making it ductile is also difficult. Why? Because of the presence of these defects already in the material, moving another new set of defects or dislocations or twins inside the material is more difficult, because the existing defects will try to put barriers for the dislocations or the motions of the dislocations or the twins. So, that is why cold working leads to decrease in the ductility, increase in the strength, but increase in the strength is okay because we want materials to have high strength, but decrease in ductility is basically not a good signature, because in the actual applications this decrease in ductility can create problem, material can actually fail miserably. So, that is why all these cold work or warm work materials are subsequently annealed or subsequently heated to temperatures, so that these kind of defect structures can be annealed out or defect structure can be rather organized properly, and that is what happens in recovery, recrystallization and grain growth. These techniques actually, these class of phase transformations deals with how to control the defect organization inside a cold worked or warm worked material. Now, question is this: as you know, just as given one example, suppose if I take a steel and piece of steel and rolled between two rollers as is shown here. So, rolling will lead to deformation of the material, so grains will become elongated and it will create all kinds of defect structure like slip bands, you can see here. This is taken from the book of Callister Materials Engineering. As you see here, mostly deformation will be anisotropic. Why? Because the grains will be oriented perpendicular to the direction of the loading. As you know, loading is happening this way, so the grains are oriented or elongated along the direction perpendicular to the direction of loading. That is obvious because in the one direction the material is getting compressed. So, that is why the grains will try to elongate in the direction perpendicular to it. And this defect structures leads to increase in the yield strength, increase in the tensile strength, but decrease in the uniform elongations and decrease in the ductility. As you see here very clearly, this is a plot between stress and strain. At the same time, the cold work is shown. Cold work means percentage deformation induced in the material. It is just like that. If I take a roll piece like that, so AD minus A0 divided by A0 is what is known as cold work. That is the amount of deformation induced. AD is the final thick area, cross sectional area. A0 is the initial cross sectional area. So, therefore, final minus initial divided by final divided by initial is what is known as the cold work. And this cold work can be represented in terms of a percentage, when you multiply it with 100. So, that means AD minus A0 by A0 into 100% is what is the percentage cold work. So, as you see here, when a cold work is less, you have a low strength, but huge low strength means stress is low to deform, but strain is large. That means material is ductile. As you increase the cold work, subsequently the stress required to deform is increasing. That I already discussed. That is the main reason for the increase of strength, because as you have more defects in the materials, you need more stress to deform it further plastically, because there are already so many defects present which will hinder the motion of the defects further into the material. So, this will lead to decrease in the strain or ductility. That is what happens in a real cold work situations. So, this decrease of ductility is the major problem in the further application of the material, and that is why they are deformed. Now, we know the prominent mode of deformation, plastic deformation, is by dislocations, and dislocations actually move by application of the shear stress. So, if I show a three-dimensional picture, this is an edge dislocation, this is an edge dislocation you see here, that is an extra row atoms, and as the shear stress is applied in this way, the dislocation moves and it reaches the surface after some time. So, dislocations, if the dislocation do not move, deformation does not happen, that is obvious, or is same thing for the twin. Twin is another mode of deformation for the hexagonal materials. Now, in a plastically stretched zinc crystal, that is what is shown here. You see here that dislocation motion leads to formation of this kind of slip bands, okay, which is formed because of dislocation motions on the surface of these crystal, and they are like that. So, therefore, in a normal material, if we measure the dislocation density, it is of the order of 10 to the power 6 to 10 to the power 9 per meter square, per meter actually. But on the other hand, in a cold work material, this can go up to several orders of magnitude higher, 10 to the power 12, 10 to the power 14 dislocation density per meter. So, that is a huge number of dislocations present inside a deformed material. 9 to 14 is 5 order of magnitude higher. Such a large number of dislocation will reduce the ductility, increase the strength. Similarly, for the twins. Now, as I said, to recover the ductility, we need to heat it up, and or rather we need to go for annealing treatment. Right here, you see here, this is the annealing treatment has been done for about an hour, and what is shown here basically is tensile strength as a function of the tensile strength as a function of the annealing temperature 100, 300, 500, 700 Celsius temperatures, and as you see, tensile strength will slowly decrease. In a cold work material, tensile strength is very high, something like about 550 MPa, but it slowly goes down, and as the temperature increases, the strength decreases slowly and reaches a flat regions at a very high temperature. Subsequently, similarly, or rather in opposite way, not similarly, ductility increases. It was very low, it is about 20%, then it increases, reaches a flat regions which is about 50% of ductility. So by by simply heating it up or annealing it, any cold work material, we can recover the ductility sufficiently, so that material can be used, or even if further deformation are required, that can be imparted. What happen, many of these deformation processes, the deformations are done in a stepwise manner. Basically idea is to, if the material has low ductility, deform by certain amount, then you go for annealing treatment to increase the ductility, again you deform. So that's this treatment, which is known as heat treatment or annealing treatment at higher temperatures, is basically made or meant for recovering the ductility by doing something. Now our task in the phase transformation, our basic things is aspect of for which we are discussing is basically understand what actually happens when you heat a material at high temperature after the cold work or after the deformation at lower temperatures. So normally things which happens in a material can be categorized into three separate classes. First one is known as recovery, second one recrystallization, and third one is grain growth. So at lower temperatures, when you anneal the cold work material, the processes which happens inside the material is termed as a recovery. We will discuss what is that in a minute's time, and then if you heat further, recrystallization happens. Now recrystallization is formation of the new grains basically, or nucleation of the new grains from the deformed grain, and subsequently if heated at a very high temperature, these new grains grow very fast. So therefore cold working of these materials leads to lot of defects, and these defects actually drive the system or material for recovery, recrystallization and grain growth kind of structures. As you say that during recovery, what is actually happens written here, recovery is basically a process in which physical properties like electrical conductivity, corrosion resistance are recovered, but not the strength. As you see, as tensile strength has not decreased much, ductility has improved little bit from about 20% to 23-24%, but strength has not changed substantially. What has changed, what will be changing is basically the physical properties like electrical conductivity, corrosion resistance, many other things. So that means something happens to defect structures in the recovery stage, which leads to improvement or change in the physical properties. So what has actually happens? As I already told you, dislocation is the primary mode of deformation or primary means of deformation in the metallic materials. So therefore during recovery the dislocations actually move little bit and find lower energy arrangements. Atoms diffuse and point defects like you have interstitials or vacancies, their numbers will decrease, or rather that means what? That means there is a rearrangements of the defect structures. That is what happens in the recovery stage. Let us discuss a little bit more. What I am showing here is for a situation of a brass. Brass is nothing but a copper zinc alloy. It is basically alpha brass, that means zinc concentration will be of the order of 40% maximum. So if you take a simple brass, deform it and then subsequently align it at temperature from suppose 300 to about 1200 degree Fahrenheit, that is equivalent to about 700-800 degrees Celsius temperatures. So tensile strength slowly decreases, as you have seen earlier, ductility improves. So what else I am showing in this view graph is that the kind of grain structures and defect structures inside the material. As you see here during recovery stage, there is some kind of a defects reorganization happens here. You can see here in this case, defect reorganization happens. That means the defect structure which represent dislocations and other things, point defects, they reorganize themselves, and then once you heat it to high temperature, something like 300 to 400 Celsius temperatures, new grains forms. That is what is known as recrystallization, and you heat it up to beyond 500, the grains grow. We will discuss each of these things separately. So let us first discuss about the recovery, what actually happens in recovery. same thing is shown here. So, as you know, any material if you deform, material is a continuous thing. That means the grains are actually continuous, they are attached to each other. So, now you are putting a stress into the material. So, as the grains are continuous, if you put a stress, only way they can be remaining in touch with each other is by deforming them or generating some kind of stress inside, and this stress which is generated because of these aspects is known as internal stress. Internal stress is basically stored in terms of a deformation energy like dislocations, point effects, that is how it is stored. So, this energy which is stored in the material needs to be removed, then only material will regain its ductility, plasticity or change its material properties. So, as you see in the ductility and increases as a function of temperature, similarly the internal stress which is present will also decrease as you slowly heat it up. So, as in the recovery stage, internal cell undergoes a huge decrease, something like 90% of the internal stress basically are removed during recovery stage simply by rearrangement of the defects. And in the recrystallization stage, the remaining part, because you are forming a new grains, remaining part is completely removed, and subsequently there will be no internal stress remain. Remember, if there is internal stress present inside the material, deforming the material subsequently is very difficult. Why? Because internal stress will resist the further deformation. Not only that, if there is internal stress present inside the material, if it is tensile in nature, it can lead to cracking of the material, failure of the material. So, that must be removed, and this is done by simply heating up. So, in the recovery stage, what we shown, the internal stress is extensively removed, and that is done simply by removing the stored energy. Okay. So, in a nutshell, what I can say, the point whatever happened in the cold work stage, the point defect density increases, dislocation density increases, this will lead to increased strength. If you annihilate, material will tend to lose this energy, and if you annihilate lower temperature, it is called recovery. If you annihilate higher temperature, it is called recrystallization. If you annihilate even higher temperature, much higher, then it will lead to grain growth, right. These are the three stages you must remember. Okay, so the annealing stage, driving force is basically what? The free energy is stored in the point defects and dislocations. That is the driving force for recovery. Because cold working lead to a lot of this defect structure, and then the recrystallization basically happens because of the driving free energy stored in the dislocations, and regain growth really happens because of the free energy stored in the grain boundaries. Because you have a large number of grain boundaries because of the small size grain forms in recrystallations at high temperature, they want to remove that grain boundaries, so therefore grain starts growing. So, as far as driving force is concerned, for the first two aspect, recovery recrystallization, is the cold work energy which is stored in the material is responsible for the transformations. But in the last stage, grain growth stage, is basically energy stored in the grain boundaries is basically used as a means for the phase transformations. So, recovery takes place at lower temperatures of annealing, as you have seen just after. In fact, in recovery these are the things happens. First thing is that there will be no apparent change of microstructures. That means there will be no change in the phases, no change in the grains size, no change in the boundaries, other things. So, that means if you see in a microscope, you will not see any change in the microstructure, because microstructure operates in a microscope. But what will happen is that the excess point defects which are created during these plastic deformation or cold working or warm working processes will be absorbed at the grain boundaries or at the surfaces, or even some of the defects like dislocations can also be removed by climbing processes. Dislocation can actually move by gliding on a sea plane, or they can climb because of diffusional processes, as you have probably studied in mechanical metallurgy. But forget about it, if you do not understand anything, these point defects or even the dislocations which are line defects, they can actually get absorbed to the surface of gain boundaries. During recovery, random dislocations, which are statistically stored number of dislocations will be there, which are opposite signs, they can come and annihilate, obviously annihilate. Dislocations which are this kind of sign or this kind of sign, they can come close and they can annihilate. Okay, very simple. This one, the top one which is shown like this dislocation, that this one has one extra row of atoms coming from top to bottom. This one has one extra row of atom coming from bottom. So when they come together, both the extra row atoms match and the dislocation is annihilated. But overall dislocations, reduction in dislocation density is very small, although they get removed. Dislocation of same sign can arrange, important aspect, dislocations of the same sign, that is for the opposite sign, they can come and annihilate. Same sign can arrange, they rearrange themselves to form tilt boundaries. Skew dislocations, tilt ones, edge ones, skew dislocation can arrange themselves to form a twist boundaries. So the formation of these low angle tilt boundaries or twist boundaries is known as what is known as in literature polygonization. I am showing the next picture in the same things. So this will lead to overall reduction in the stored energy. So what is polygonization? Okay, let us look at it in a very brief way. You know that in a store, in a basically deformed material, you have a lot of energy, plastic deformation energy or strain energy stored by in terms of dislocations. These are all dislocations of same type, okay, edge dislocation of same type. Now statistically stored edge dislocation in a crystal can actually can lead to huge amount of energy stored, and this is what is the reason for the decrease in ductility. So now what can do this dislocation? This dislocation can actually easily arrange on top of each other. Instead of arranging on a line, you see they are arranged on 3 different lines, they arrange on vertically. Okay, these things are coming vertically top of each other. Okay, so as they arrange vertically top of each other, and so therefore they form low angle tilt boundaries. Very simply, if we go back my own lectures in this course about the boundaries, tilt boundaries, twist boundaries. Tilt boundary is nothing but a vertical arrangement of the dislocations. So this is the way these dislocations can actually arrange nicely, and this is known as polygonizations. This has been observed in the actual literature, actual microstructures. So polygonization is a means to decrease the stored energy. As you see here, we have not decreased the number of dislocations or density of dislocations by this process. What is happening here is basically rearrangement of the dislocations in a certain specific manner, so that the energy stored in this part of the crystal is removed. Energy is basically rearranged along in terms of the dislocations lining along the vertical line. Okay. So obviously this leads to change in the physical properties. One of the physical property which is important is the resistance or conductivity. Inverse resistivity is not a conductivity. As you see here, let us look at the cold work material, this one which is given by this line. So there are several stages of this change in the cold resistance. Initially resistance will not change much if you heat up to room temperature, but as you go beyond room temperature there is a drastic change. This is for lead actually. There is a drastic change of the resistance, drastic decrease, because that is obviously initially there are lot of defects. So resistivity was very high. As the defects get rearranged, resistivity decreases slowly. So and similarly for the other samples, like if you look at basically you can actually have other stages. You see here there are stage 1, stage 2, stage 3, stage 4, stage 5, stage 6, but here there are actually 3 stages, 1, 2, 3. So depending on the type of materials, how the dislocations get arranged, how these point defects get arranged, there will be different number of stages, that is possible. But important aspect is that physical parameters do get changed, not the microstructural parameters. That is what you must understand. Now how we can actually do that, measure it? We can measure it using X-ray diffraction basically. This is at annealed sample at different temperature, 375 to 475 degrees Celsius temperature at different time scale up to about 10,000 minutes. What is plotted here is basically the for the ratio of the FWHM or full width hub maxima for the cold work for the two materials, one is annealed, another is cold work. Okay. So, this is the ratio is plotted. As you see, the ratio is slowly decreasing as you go along the time scale. So, that means what? That means that the strain inside the material is slowly decreasing, because the full width hub maxima in the of the peak in X-ray diffractions, it tells you when the grain size is not changing much, it tells you the strain induced in the material. So, this is the way one can actually calculate the strain, reduction of the strain in the material. So, let me stop here, but let me just tell you that we have simply discussing or whatever we discussed today is that cold working is inevident in the material processing. Many of the materials are cold work because we need to give shapes, and this cold work leads to a lot of defects, generations of the material, and defects will lead to decrease in the ductility and many other properties like toughness. So, in order to regain that, we need to anneal it at high temperatures. During annealing, you can have many kinds of possibilities, like you can have reorganization of the defect structure, which can lead to recovery. You can also generate new grains inside the material, which is known as recrystallizations, or because of these grains are very small, they can grow at high temperatures. What is can happen is known as grain growth. Recovery is the first step in these annealing techniques. Recovery leads to reorganization of the defect structure without much change of the microstructure, and this leads to change in the physical properties like electrical conductivity, resistivity, or corrosion resistance. So, we will discuss more about recovery a little bit more, and further we will discuss about recrystallization in the subsequent lectures.